No, you're still going to have proofs. They just are going to be different kinds now. Okay. So your objective today is to learn about something called concurrent lines. So we're going to understand concurrent lines and the theorems about them. So even though this comes from chapter 10, excuse me, you still have vocab and theorem cards that come from this chapter that are going to be part of the chapter 11 information. So this actually comes from lesson 10.3 in the book. Now remember, chapter 10 was all about the constructions. So that means at this point, we're done with constructions too, because we've done them all throughout the year. So let's start with our vocab word. What are concurrent lines? They are two or more lines that intersect in one point. Now, last year, and even this year, you've done it as well. What did you deal with that would be described as concurrent lines? Go deeper. Not just perpendicular lines. We studied a whole chapter on this in our algebra class. Dealt with concurrent lines. So two or more lines that intersect in one point. What is that describing? No, parallel lines actually never intersect. That's about as opposite to this as we can get. Okay? We spent an entire chapter on this. Majority of our word problems use the notion that we learned from this chapter. Dakota? No, not even. No, those aren't lines, babe. Nope, we already got that once. Y'all don't remember system of equations? And that system of equations are two lines that are written in the same variables, and that what you're solving for, that ordered pair, is the point of intersection. It is that point of intersection. We spent this much time on the graphing portion, and here's the interesting thing. In Common Core, it's huge. That notion of graphing becomes now humongous with Common Core, and in the old algebra class, it was very small because it's a very inaccurate way of finding the intersection if you're doing it by hand. But if you're using technology like a graphing calculator or a program like Desmos, then you can be extraordinarily accurate at those points, for those points of intersection, using that technology. We got more into the algebraic ways of solving the systems, and you've been using those algebraic ways as well in this class, trying to solve when you had two variables in your equations. So system of equations is describing concurrent lines because they do intersect. But what's interesting is now we may be talking about more than two, because it says two or more lines. So now we're talking maybe 3 lines or 4 lines or 5 lines. Okay, so first theorem for this group. Theorem 10-1 states this. The bisectors of the angles of a triangle intersect in a point equidistant from the 3 sides of the triangle. Okay. So let me draw a picture of our triangle. And if I bisect each of these angles, what we find out is that those bisectors all intersect in this point. Okay, let me put some letters on my triangle. We'll call it triangle ABC. And so from this theorem, what it says is that R is equidistant it's the same distance from each side. So from segment AB, segment AC, and segment BC. Okay. So to prove this, we would be using some old theorems. Would be proof uses theorem, 4.7 and 4.8. And to refresh your memory, theorem 4.7 says, if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. And if a point is equidistant from the sides of an angle, then the point lies on the bisector of the angle. So back from chapter 4 is going to help us prove this out. Okay? So that's the first one. Next one. Theorem 10.2. It states that the perpendicular bisectors of the sides of the triangle intersect in a point that is equidistant from the three vertices of the triangle. Okay. So this is saying if we have a perpendicular bisector, that means it's got to be at a midpoint. No, it doesn't necessarily go through a vertex. It's got to go through the midpoint and is perpendicular. So this point, which again we'll call R, and our vertices are A, B, and C. So according to this theorem, it says R is equidistant, or the same distance, from points A, B, and C, the three vertices. So the proof on this guy it uses theorems 4.5 and 4.6. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So theorem 4.5. And then 4.6 is its converse. Okay? Then we have, let's see, we talked about angle bisectors, perpendicular bisectors, so the only one we haven't talked about is altitudes. So that's the next one. Theorem 10.3. And it says the lines that contain the altitude, the altitude of a triangle intersect in one point. So altitudes do go from a vertex and are perpendicular to the opposite side. So again, this would be your point R. And you would say, that's it. R is, there's nothing much to say. That's the point of intersection. Of the altitudes. Okay. Now, the most important one is the next one, and this is the one that you're going to see used a lot. This is Theorem 10.4. Which says the medians, so that's the last one we hadn't talked about, of a triangle intersect in a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So let me draw a quick picture of that. So remember what midpoints are. They go from a vertex to a midpoint. So this point of intersection. What they're saying is that, and this is NMO, is that N is the midpoint of segment AC, M is the midpoint of segment BC, give me just 1 second, O is the midpoint of AB. If this is the case, then the length of AM or AR is equal to 2/3 the length of AM. The length of BR is 2/3 the length of BN. The length of CR is 2/3 the length of CO. In addition, we could get this, that the length of RM would have to be 1/3 the length of AM, and so on. That is going to show up in a lot of problems. So make sure that this one is the most important one. All right, that's it.